So I'd like to thank the organizers not only for inviting me, but actually for allowing me to speak about something that's not directly QCD. But as you will see, it's related to the dynamics of strongly coupled gauge theories. For some reason, there we go. So as you know, we discovered gravitational waves, as you've heard. And that opened not one, but two experimental windows into the universe. One is into the strong field regime of general relativity, and the other one is into the properties of quantum matter. Now, these two aspects are normally, actually quite often intertwined. For example, if you think about neutron-star mergers, as we just heard, what you're describing is quarks and gluons, which are described by quantum chromodynamics, interacting in the presence of a very strong gravitational field sourced by the quarks and gluons themselves. Now, in some cases, the matter involved in these scenarios is standard model matter, like in the case of neutron stars. And in some other cases that I'll talk about, this could be beyond the standard model matter, as in the case of cosmological phase transitions. Now, this is a good opportunity for holography, because if we want to maximize the discovery potential, we need to understand the dynamics of quantum matter coupled to dynamical gravity. In fact, this matter is often strongly coupled and/or out of equilibrium. And in these circumstances, holography is sometimes the only first principle tool that you have available, at least to try to understand the qualitative physics. So what I would like to do today is just to give you an overview. I'm not going to get into any sort of details, and I'm only going to use pictures to try to walk you through something that is very embryonic at this point. This is a very early stage of development of these type of applications. So if you have, I realize this is outside the main theme of the workshop. So if you have questions, please, you don't have to wait until the end, just interrupt me. So the plan, now that I've given you the motivation, is I know that we've heard about holography quite a few times, but I want to get everybody on the same page. So I'm going to spend 1 or 2 minutes to tell you everything you need to know about holography to follow the rest of my talk. Then I'll focus for the most part on cosmological phase transitions. And I will describe two mechanisms by which this can happen. One, the first one is very well known. The second one is new. And in this part of the talk, I'm going to take the approximation in which I'm going to ignore the expansion of the universe. You should imagine this is a cosmological phase transition. But if the time scale for this is fast enough compared to the expansion rate, you can just imagine as a first approximation that this is happening in flat space. And that's what I'm going to do here. But of course, that's only an approximation. And in the second part, if we have time, I'll tell you about an extension of the usual holographic framework in which you can actually treat strongly coupled matter out of equilibrium coupled to dynamical gravity. And if time permits, or if you ask me over coffee, I can tell you about possible applications to baryogenesis, primordial black holes, reheating, and thermal inflation. Are there any questions? Okay, so what is holography? Holography is the following statement. It is the statement that in some cases, some quantum field theories formulated ordinary quantum field theories with no gravity, like QCD, for example, formulated in Minkowski spacetime in 4 dimensions, are completely equivalent to something that looks very different, which is, for the purpose of this talk, just classical gravity. By this, I mean Einstein's general relativity in a 5-dimensional spacetime, which is a little strange. It's called anti-de Sitter space, or in a more general case, it asymptotes to anti-de Sitter space. You don't need to know what this is. It's just some curved spacetime in 5 dimensions. And the statement is that by doing classical gravity here, in principle, I can answer any quantum mechanical questions about your gauge theory here. That's the statement. It's an equivalence, okay, between two seemingly very different mathematical descriptions of the same physical reality. Now, one important point is that this space has the property that the boundary, the asymptotic boundary, is isomorphic to Minkowski in 4 dimensions. And for this reason, it is extremely convenient to think of your quantum field theory, which is defined in Minkowski space, as living at the boundary of this space. So in that case, if you think about it in this way, this is actually a realization of what's called the holographic principle. The holographic principle tells you that a theory of quantum gravity in some volume is equivalent to a non-gravitational theory living at the boundary of that volume. Okay, that's the statement. Now, there are two more things you need to know. One is that if you're interested in thermal states, let's say you want to look at properties of the quark-gluon plasma, in your gauge theory, in your four-dimensional ordinary quantum field theory, those are encoded. So everything in here has a translation over here and vice versa. That's what equivalence means. This is encoded in the properties of some black hole sitting at the bottom of this space. This is quite plausible because you know that black holes have thermodynamic properties. They have entropy density, energy density, et cetera, et cetera. So this would be what you would do if you were interested in equilibrium physics, okay? The equilibrium properties of your plasma are related to equilibrium properties of a static black hole. But, and this is the absolute key point for this talk, you can go beyond that and you can ask, what does the regime of really far from equilibrium quantum field theory in this side correspond to in this side? And the answer is, it corresponds to classical gravity, so Einstein general relativity, but in the strongly time-dependent regime, okay? Out of equilibrium means time-dependent. And because this is quantum mechanical, but this is classical, here's where the power of this correspondence is. If you want to understand out of equilibrium quantum field theory, at least for these cases in which we know the gravity dual, what you need to do is something that's still hard, solving Einstein's equations in 5 dimensions in the presence of time dependence, but it's a classical problem. It's much simpler than this. We know how to evolve in time Einstein's equations. Yes?
I thought the correspondence is exact only in large time.
No, this is not correct. This is
It's good if you repeat the question.
Sorry, yes, I apologize. The question is whether this correspondence is only correct at large n in the planar limit. Let me say, since you asked, actually I have a disclaimer. Let me postpone this for 30 seconds. Because I wanted to say that for the purpose of this talk, you don't need to know any of the details of how this works. You could just think at the most operational level of this 5-dimensional classical description as a computational tool that will allow me to translate difficult problems, quantum mechanical problems here, into some other language where I can solve the problem and then translate back. Okay, so it's just a fancy exotic computer, if you like. And now the disclaimer, coming back to your question. So first of all, we do not know the dual gravity description for every quantum field theory, okay? So if you ask me, what is the dual of QCD with 3 colors and 3 flavors? I don't know. And not only that, but I do know that actually, if I go away from large n, so the correspondence is supposed to be true for any n and any value of the tooth coupling lambda. But it is only powerful for my purpose in this talk when you are at large n and strong coupling. Why? Because if not, I cannot just use classical gravity in this 5-dimensional space-time. I have to do full quantum gravity. Okay, quantum gravity corrections go like 1/n, are suppressed by 1/n. So the planar limit in the gauge theory is the classical limit on the gravity side. Okay, but this is not a, this is just a limitation of my computational power. I don't know how to do quantum gravity or string theory if you want. Okay, but the correspondence is supposed to hold for any value of n and lambda. And because I don't know the dual of every quantum field theory, all the statements I will make in this talk are true for quantum field theories for which I know this gravity dual and I can use this tool, okay? This is not all the quantum field theories, but this is the hope. Since it is a large class, the hope is that if we look at sufficiently generic properties or qualitative properties, we can learn something that may be applicable more generally, robust properties, okay? That's the idea. Any questions? Yes, please.
Are there QFTs that do not have a gravity dual?
There are QFTs, sorry, yeah, the question is, are there QFTs that don't have a gravity dual? Indeed, any finite n theory is not dual to a gravity theory. It's dual to a string theory.
I rather meant whether there are
there are lots of quantum field theories for which we don't know how to make a statement, but I don't know of a proof that there isn't such a dual thing. Any other questions? Yes, please. Okay, the question is, which is the most realistic quantum field theory for which we know the gravity dual? The most realistic is a very, relatively, let me say, relatively subjective thing. What I can tell you is that the regime we know how to analyze, like I said, let me just repeat it, on the string theory side easily, is the regime in which in your gauge theory, you go to the planar limit, so large N, and the tooth coupling is strong. If you ask me, for example, about large N, but weakly coupled QCD, that is not described by classical gravity, that would be string theory. Okay, so the limiting factors here are, it's good to keep this in mind, that when I use classical gravity, I'm assuming that the dual gauge theory is large N and strongly coupled. Okay, strongly coupled is not necessarily bad. Large N, for some purposes, maybe a weaker or stronger limitation. We can discuss that. Yes.
And is it important to have gauge theory? I mean, you say QFT there. You can have QFTs which are not gauge theories. What's the
Good.
story there?
So again, to have a controlled limit on the gravity side, actually to be able to use gravity, I need the central charge in technical terms in the quantum field theory to be large, because 1 over the central charge is going to suppress quantum gravity corrections. So if you have an SUN theory, the central charge is n squared. So if you take n squared to be large, but if you tell me a quantum field theory with no parameter that I can scale to be large, then that probably has a very complicated quantum gravitational description on the other side. Okay, so for the purpose of this talk, we are going to be talking about the planar limit and strong coupling. But the advantage is that once we accept that limitation, we can do arbitrarily far from equilibrium physics. That's the trade-off. Any other questions? Good. So let me talk about the first topic, cosmological phase transitions. And I will, by the first mechanism, which is bubble nucleation, which is probably something you're all familiar with. But nevertheless, let me say a few things. So as you know, first order phase transitions happen everywhere in nature. For example, when you boil water, and one way in which they can happen is through the nucleation of bubbles of the preferred phase inside the metastable phase. So you can ask whether this happens in particle physics. If it does, this would be very exciting because, as you know, the history of the universe is basically the history of particle physics at every possible scale all the way up to inflation. So the universe would have undergone this phase transition. And the reason this is exciting is that this would have nucleated bubbles, which would have expanded and collided. And this process would have produced gravitational waves, which in some cases could be detectable in the near future. For example, if it happens at the electroweak scale or nearby, this could be detectable by LISA, which is a mission that will launch sometime in the next decade or so. Now, in the standard model, we believe there are no first order phase transitions because both the QCD transition and the electroweak transition are believed to be crossovers. If you're a pessimist, this is bad. But if you're an optimist like me, this is great news because it means that the discovery of gravitational waves coming from a cosmological phase transition will amount to the discovery of physics beyond the standard model because there are no phase transitions in the standard model. And not only that, in fact, it may be our only window into the energy scales associated to this phase transition. So in fact, in the standard model, strictly in the standard model, the electroweak transition is a crossover, but even minimal extensions of the standard model tend to give rather easily rise to a first order phase transition. And as I said, the signal is in the right range of frequencies to be detected by LISA. Okay, and it seems that the amplitude is also could be large enough to be detectable. And for this reason, there's a huge amount of work that has been devoted to studying what happens if there was a phase transition in the universe at a scale around the electroweak scale. Okay, and rightfully so. But for today, I would like to broaden the focus and keep in mind that the phase transition could take place. We don't know what lies beyond the standard model. Okay, so it could take place at any temperature well above the standard model, the electroweak scale. And moreover, it could take place not even in the visible sector, but in some dark sector. So the temperature of that phase of that sector may not even be the same as the temperature in the visible sector if they interact very weakly. Okay, so keep in mind that there's basically a huge amount of things we don't know, so it's good to keep an open mind as a theorist. Okay, now I've been talking a lot about first order phase transitions, and I know you all know what that is, but let me just flash this slide to put everybody on the same page, because this will be important. So what does it mean that we have a first order phase transition? It means that if you plot the energy density as a function of temperature, you will see this multivaluedness. Okay, you will see that there is some critical temperature. The blue states here will be absolutely stable. These ones here, between the critical temperature and this turning point and here, will be metastable. Those are supercooled or superheated phases. And then these in between, these are unstable. That's called the spinodal region that we just heard about this morning. Okay, very good. In terms that you may be more familiar with, in terms of an effective potential, this region and this region correspond to the case where there's only one minimum available to the system in the effective potential. Only one state is available at that temperature. Whereas in here, you have two minima. One of them is the absolute minimum. The other one is the metastable minimum. And a maximum in between, which is unstable, which is this spinodal state. Is that clear? This picture is important. Good, people are nodding, so good. Now, what is this transition? So how does the phase transition take place in the universe? One picture is that as the universe is expanding and cooling down, it will eventually cross this critical temperature. And then at some point in this metastable phase, it will begin nucleating bubbles of the preferred phase, which is this one. How fast or when this happens depends on the nucleation rate, which is controlled by this tunneling between the metastable and the absolutely stable minimum. Okay. And the key point is that once you nucleate these bubbles, and you nucleate many of them in a Hubble patch, they will expand and collide, and that will produce gravitational waves. So the gravitational wave spectrum, which is what we really want to know, because that's what you would measure, is sensitive to many parameters, microscopic parameters of phase transition. But the one it is most sensitive to is the velocity with which these bubbles expand. This is called the bubble wall velocity. And interestingly, this is not only the most important one, but the hardest one to compute. Why? Because this is not an equilibrium property. Okay, this is not like a latent heat that you can get from thermodynamics. The wall, when it's expanding, it's pushing out the plasma in front of it and it's heating it up. This is an out of equilibrium process. So computing from first principles this velocity, even at weak coupling, is extremely difficult. However, it can be computed extremely easily, or relatively extremely easily, in holography. And that's what I want to show you. So the strategy is to follow what I said at the beginning. So I want to do a calculation in this strongly coupled quantum field theory that is supposed to have a first order phase transition. And I want to compute with what velocity this bubble of stable phase will expand. But I don't know how to do a calculation here. But I can map this problem to a classical gravitational problem in 5 dimensions. And here I only need to solve Einstein's equations. So I set up the analog of this bubble here, which will be some bump in my horizon. Remember that the thermal state is a black hole. And then I let it go. And because the pressure here is bigger than here, it will expand. And in order to see how it expands, I need to solve or evolve in time my 5-dimensional Einstein's equations. Okay? But that I know how to do. And once I've done that, I can translate back. And what I will read off, the simplest thing that you can read off, is the time and space evolution of the stress tensor in the boundary gauge theory, which is what I was interested in. So let me show you what happens. What I'm plotting, I'm going to show you a video. This is the initial bubble. This is all gauge theory or quantum field theory information. There's no 5-dimensional gravity or anything. It's the result of a calculation in 5 dimensions, but it's expressed purely in 4-dimensional terms. So here I'm plotting for you the energy density, and here is X and Y. Okay, I'm taking a slice. And the video will show you the time evolution. So this is the initial bubble. The pressure inside is bigger than outside, so it expands. And simply by taking delta X over delta T, you can read off the velocity of the wall. It's trivial. What's that? No, this is the color coding is energy density. Yeah, energy density in the gauge theory. Yeah. This is the what hole? Oh, this. No, I think this is either an optical. There's no hole in the middle. Yeah. Actually, to be completely honest with you, there is a hole, but explaining that would take me a long time. Okay, and there is a good reason why there's a hole, which has nothing to do with anything I've said so far, which is completely irrelevant for this talk. But I can tell you, it has to do with proper. Well, anyway, let me not do that. But we understand what the hole is. Just ignore it. Okay, so by doing this simulation for different nucleation temperatures, okay, you can, for example, plot the velocity as a function of the difference in pressures or things like this. So this plot, which is preliminary, is the first calculation ever of the bubble wall velocity in a strongly coupled gauge theory in 4 dimensions.
The simulation is some kind of finite element method, or it's, I guess, non-trivial too?
That boils down to your favorite method of evolving Einstein's equations, discretizing them, putting them on a computer, and so on.
Yeah, but what is your favorite one?
So we use the characteristic formulation, okay, so null slices, and then we use spectral methods in one direction, finite differences in another. There's a whole. This is all published, by the way, if you want to look at the details. Yeah. Now, of course, if you want to compute the gravitational wave spectrum from these collisions, you can't just look at a single bubble. You have to look at multiple bubbles. So let me show you what happens with 2 bubbles, because now you will see them collide. Again, this is energy density as a function of position and time, and it's the result of translating into the quantum field theory the 5-dimensional calculation. Okay, so this is work in progress, but what I want to emphasize is that in this description, there are no approximations in the sense that all the post-nucleation dynamics, and that means the bubble expansion, the bubble collisions, all the sound modes that propagate in the plasma, the possible appearance of turbulence, all of that is included. So that's interesting because the conventional treatment of this problem includes assumptions and approximations. Okay, for example, the use of hydrodynamics and other assumptions. With holography, you can reformulate this, at least for certain quantum field theories, and that allows you to compare and check in this particular class of models which assumptions are justified or which ones are not. Okay, let me move on to the second mechanism. Of course.
I assume that the simulations and gravity side is all dimensionless.
Is all what?
Done with dimensionless quantities. How do you connect it to something physical in physical units?
Good. So,
can you repeat?
Oh, sorry. Yes, I keep forgetting. Sorry. The question is, on the gravity side, everything is done in a dimensionless way, in the sense that we put it on a computer. How do we translate to physical units in the quantum field theory? Let me say this is always true. It would also be true in the quantum field theory. Anything you put on a computer, like when you do a lattice simulation, everything is dimensionless. So the question is not how the question is not the computer. The question is how I translate from units in 5 dimensions to units in 4 dimensions. And the answer to that is that, for example, what you would call the QCD scale, in other words, the critical temperature, what determines the critical temperature in the gauge theory, corresponds to a boundary condition for one of the fields in 5 dimensions. So by fixing that boundary condition, it's a coefficient, by fixing that to 1, I'm saying that I'm measuring all my quantum field theory quantities in units of TC, for example. I can give you more details, but it's a trivial thing once you know how to do it, but it's a good question.
It's highly non-trivial if it happens at the boundary condition. So you have to decide that.
Yes, indeed. Yes. You just choose that you're going to measure everything in units of lambda QCD if you want. My picture disappeared.
Your picture disappeared.
Ah, okay.
Picture mean yes. Now it's appeared.
Better now?
Yes. Now we see you.
Yeah. Okay.
Just go on.
Shall I keep going? Okay, good. So what I showed you is one way which is very well known in which the first order phase transition can take place. What I want to point out here is that there is another mechanism that can take place if the gauge theory under consideration has a large number of degrees of freedom. So if you imagine that beyond the standard model, there's some grand unified theory or some other completion at some energy scale that has a large number of degrees of freedom, or for example, some dark sector, okay, then you know that this nucleation of bubbles is suppressed. Why? Because to nucleate a bubble, you need a coherent fluctuation with a finite size of all the degrees of freedom involved in the phase transition. If you have many degrees of freedom, that is more and more unlikely, the larger the number of degrees of freedom. And in fact, if you look, for example, at a large chain gauge theory, then this probability, this nucleation probability, is suppressed exponentially with n squared, okay? So if you imagine a scenario in which there's some large n sector beyond the standard model at some scale, it's interesting to consider what would happen. And what would happen is that because you suppress the nucleation, the universe can actually evolve along the metastable phase and enter the unstable phase. And at that point, there is a classical instability, not a quantum tunneling. Just some sound modes here become unstable at the classical level. If you just slightly perturb the plasma, this cosmological fluid, these modes will evolve exponentially, and they will drive you away from here. Good. Now, the initial evolution of those modes is described by linear theory, okay? Because you start from an unstable equilibrium state, and they will grow initially exponentially. But very quickly, the dynamics becomes nonlinear. So you need some method to evolve these nonlinearities in this strongly coupled gauge theory. And holography can do that, and I will show you the result, provided you ignore the expansion of the universe, okay? So if you imagine you're in flat space, then I can tell you what happens, and this is what happens. This is a slightly longer video. This is the end of the linear regime here. Everything beyond this point is nonlinear. So this is a slightly longer video. Thank you. We're going to go up to T of order 1100. So please bear with me, because I want you to see this is a real-time evolution in a strongly coupled quantum field theory, okay? Which is going to lead to a separation of phases. So what you saw is that the initial evolution is very fast. It's an exponential behavior. And then once the nonlinearities appear, everything slows down. We're almost there. Okay, so this is a phase-separated state with an average energy density corresponding to this point, which was the homogeneous initial state that was unstable. So if you evolve this in a box with fixed energy density, as we did, the final state is a phase-separated state in which you have phase coexistence. This phase in here corresponds to this one at TC, and this one outside is this phase, which has a higher energy density, but the same temperature. So the temperature is constant across the whole volume, even though the energy density changes, as it would be if you have an ice cube floating in water at 0 degrees.
That's stable? Is it stable?
For a fixed box, this is now stable because this maximizes the entropy density. For a fixed box with fixed energy density, okay? Yeah.
But not the position of the bubble, that can be.
Yes. Yes. Well, in a fixed, actually, in a sufficiently large box, that would be true. So the question was whether the bubble can be anywhere. Here, the volume effects, because as you see, the size of this domain is comparable to the size of the box. But, and by the way, this fast redistribution of energy because of this instability leads to the production of gravitational waves, which we computed. This little bit here is the linear regime in which these things grow exponentially, and everything else is nonlinear, okay? And nevertheless, actually, this plot is not very relevant for cosmology. Why? Because what I showed you, this video, happens on a time scale and on a length scale, which is typically much shorter than the inverse Hubble rate. This means that this basically happens in flat space. It doesn't know anything about the expansion of the universe, and it will give you a tiny little corner in your huge Hubble patch. So the result is that at the end of the video, if you simulated this over the entire Hubble volume, you will get many copies of this. And then the following dynamics will be completely nonlinear, and it will tend then to, it's like putting many copies of this system in a bigger box. These domains will tend to join together and form a bigger one. Okay, but that evolution is very nonlinear, and we're looking into that. I don't have the answer yet, but that's what's going to produce a visible or detectable gravitational wave signal, because it will be radiating for a whole Hubble time or many Hubble times, as opposed to a microscopic time. I hope that's clear. Good. How much time do you have? 5 minutes? Okay, perfect. So everything I have told you, by the way, are there any questions since I have 5 minutes before I move on to the next topic? Okay, everything I have said so far is about using this 5-dimensional gravity to understand the dynamics of a strongly coupled quantum field theory in flat Minkowski space, which is fixed, okay? There's no dynamical gravity. And in fact, the space-time is flat. But of course, there are many problems, many interesting problems that require coupling your strongly coupled quantum matter to dynamical gravity. For example, neutron stars. Or cosmological phase transitions, if you want to go beyond the approximation that the universe is not expanding, etc. Primordial black holes, reheating, etc., etc. Pretty much everything in cosmology requires a dynamical space-time. In that context, what you really want to solve is what's called semi-classical gravity, which is Einstein's equations coupled to the expectation value of a quantum system. For example, quantum chromodynamics or some other gauge theory. So if you want to do that in holography, you need to extend the usual framework to allow now for a dynamical gravity where your gauge, your strongly coupled quantum field theory is propagating, okay? So this is now a coupled problem. You have classical gravity, so your boundary is fluctuating. By that, I mean evolving classically. And it's coupled to the dynamics of some quantum stress tensor, which is also back reacting on the evolution of the metric. This is exactly what happens in a neutron star merger. Okay, quarks and gluons are described by quantum chromodynamics, but they are sensitive to the fact that they are in a non-trivial metric, and their dynamics will also change the metric. So we actually found a way of describing this by extending the holographic framework, and the idea is extremely simple conceptually. It is the following: you simply use 5-dimensional classical gravity to evolve in time the quantum stress tensor of your quantum field theory. And then you use the classical Einstein's equations at the boundary, coupled to this source, to evolve your boundary metric. This is, of course, easier said than done, because these two are coupled. Okay? So I can tell you the details if you're interested, but they're conceptual, potentially conceptual stumbling blocks that we thought about for a long time, but in the end, it actually works. And just to show you an illustration, this is purely for illustration purposes. This is the evolution in time of an FLRW cosmology, where the only degree of freedom in the metric is the scale factor, coupled to out of equilibrium quantum matter. Okay, so the different curves here are the ratio of pressure to energy density for different initial conditions. For example, this one, the blue curves are the exact evolution that comes out from holography, which includes all of these non-equilibrium effects. Whereas the ones in red or green are the ones you would get by simply evolving this scale factor, as cosmologists usually do, using the ideal equation of state, which knows nothing about out of equilibrium physics. And the fact that they only agree at late times, but not at early times, is showing to you that initially at early times, out of equilibrium effects are important. This is just to show you that this can be done. Okay? That this framework we proposed actually, at least in the most symmetric scenario, does work. Good. How much time do I have? 1 minute? Yeah. Okay. So let me just say something about baryogenesis, and then I'll stop. And if you want to know about the other topics, you can ask me. So as you know, we are here because there are more baryons and antibaryons in the universe. And how this asymmetry came about is something we don't really understand. But we know that in order to produce it, we need to, at some point in the history of the universe, these Sakharov conditions must have been fulfilled. And one of them is that you need to depart from thermal equilibrium. And for this reason, one of the proposals for a mechanism that could realize this is that if there is a cosmological first order phase transition, as I told you, the dynamic near the bubble wall is out of equilibrium. So that could be a place, as this sweeps out, your entable Hubble patch, this could be creating this baryon asymmetry. That's one of the mechanisms that has been proposed. But one difficulty with this is that it's actually very difficult to compute the asymmetry that you would generate precisely because it's out of equilibrium physics, okay? So what I want to point out is that actually with holography, using these simulations that I showed you, you can actually do a first principle calculation of this asymmetry that gets generated, okay? This is work in progress, and it will appear at some point. And not only that, but in fact, now you could think of another mechanism, because this spinodal instability I told you about is also out of equilibrium physics that could take place in a large N phase transition. If this happened, then this would also generate baryon asymmetry, okay? So let me stop here in the interest of time, right? Okay, and if you have questions, I can answer them or I can tell you more.
Thank you very much.